Why didn't the functional programmer use an array? Because they couldn't make head or tail of it. No one? I'm Ray Myers. Welcome to Craft versus Cruft. And if that joke doesn't make sense to you now, it will in a few minutes. So, I would like to revisit the Dafny programming language, which is a proof-aware language that is capable of making verified code and then transpiling it to a number of different target languages like C#, Java, Go, JavaScript, and Python, I believe, are the ones. So a wide variety of languages that you can get verified code into once you've made it in Dafny. And I had a previous episode where I did the Gilded Rose refactoring kata in Dafny, kind of using the proofs as a more generalized form of unit test that you would normally use to drive your refactoring in that exercise. I've been seeing a bizarre uptick in posts about linked lists lately, and so I thought that would be a good one to go back to, even though this is really just intro to computer science class stuff. A lot of us did this in college if that was our path, and then kind of forgot about it, at least on an implementation level. Hopefully you remember how they work. And in particular, some people are saying, hey, linked lists are really hard to implement. Some people are saying they're really easy. Usually they're thinking about implementing it in a C style. As you're going to see, the logic's the same when we're going to implement it in Dafny, but it looks a little different because we don't have pointers. Leaning into the strength of a language with lots of verification capabilities, I'm also going to write this in a purely functional style, which will work for a singly linked list. If we wanted to make a doubly linked list, then we wouldn't be able to use a functional style. Maybe I'll show that in a future episode. We still could do it in Dafny, though, because you can do imperative code there, too. In addition to just implementing the data structure, which you can find on anyone's channel, we're going to put a twist on it, which is why we're doing this in Dafny, because 2024 is the year of formal methods, remember. So we're going to implement these verbs, and we're also going to do proofs about them. I'm not going to prove every single property that these might have. We'll pick some along the way. So when you choose some properties of these verbs to specify, they are going to be enforced at compile time. We will know exactly how this is going to behave, and that'll hold for any input whatsoever. So kind of like a generalized form of a test. So again, what you're going to see here is a pretty basic implementation of a singly linked list, but done in a purely functional style. And we're going to use formal specification and verification to demonstrate at compile time that certain, correctness properties and invariants hold. So let's get started. First thing we're going to need is just the actual structure that we can store a linked list in. I'm going to adopt the naming conventions that we would see from Lisp, but you don't have to call them the same thing. In Lisp, we have something called a cons. And a cons consists of a head and a tail. Or the native tongue, they call them the car and the cooter. And when you're talking about a list, they can also be the first element of the list and the rest of the list. So this is all the same thing. I'm going to use head and tail. So we started up a little module in our Dafny file. We've got the Dafny extension in VS Code, so it's going to do all the verification right here in the editor window. We're not going to have to move around a lot. So let's define a little data type here. I'm going to call it list. We're in the linked list module, so that's the kind of list all this stuff is going to pertain to. And we're going to say that this is going to have one of two things. It's going to be nil, which is null in Lisp, and it is how you signify the end of a list. Or it'll be a console, which consists of a head, which is some kind of element. So if it were a list of natural numbers, that's nat in Dafny, and then the tail, which is going to be not another console necessarily, but another list. So either another console or a nil. Boom, we've got a singly linked list of natural numbers. Now, we don't want to be constrained to only storing numbers in this. So of course, we've got our generics. So I'm going to say a list of type T, can have a console with head, element, of type T. Now we have a generic singly linked list that can hold any old thing. So let's start to define operations on it, right? Like, because obviously that's not the hard part of making a linked list. Now, in a singly linked list, pretty much every operation is just going to involve iterating through the entire list in linear order. So there are certain kinds of things that data structure is efficient for, certain kinds that is definitely not, and you would be better off using an array or some other thing. But you're going to notice that as these go through, they're all just sort of doing a linear traversal through this. So let's define a function for length. Now there is a difference in Dafny between a function and a method. Function in Dafny means pure function. It's not going to modify anything. So it's the length, and it's going to take an li, which is of type list. And what do you get out? You probably get out a natural number, 0 or more, is what comes out of a length. So now, to deconstruct this kind of algebraic data type in Dafny, you'd want to use a match statement, which is very much what you'll find in the ML family of languages, like OCaml and Haskell and Rust. Haskell's syntax for it and pattern matching is just amazing. We have some decent syntax here. It's not quite as good. So we're going to match li, right? And it's one of two cases. It's nil or it's cons. Well, if we pass in nil, then the length is 0. That's pretty obvious, right? And we have another case, which is that it could be cons. If it's cons, then it has a head and a tail. So what's the length if it's a cons? Well, I guess it is whatever the length of the tail is plus 1. Right? So, boom. I mean, that verifies, but we haven't really verified anything other than the kind of intrinsic properties we get, right? It's is capable of accepting a list. It will always give you a nat if it gives you a list. It doesn't say it explicitly, but it is also proving termination. So this can never just loop forever. That is something the green check mark is telling us in Dafny. We would have to override it. The default behavior is your program must terminate. That is actually interesting in this case because it tells us that we couldn't be giving it a cycle in a linked list. Now, that may seem counterintuitive to you if you've also done this exercise, for example, in C, where you can juggle pointers in order to create your linked list, because that would allow you to make a linked list with a cycle in it, and length could just go on forever and never terminate, or more likely overrun the stack as it's written now. And so to detect if that were the case, you would have to even use something called the tortoise and the hare algorithm, which involves iterating through a linked list using two different pointers that are going at different speeds. And if they ever hit each other, you know that you've got a cycle. Strange but true. But we're not checking for that here, and it proves that it does terminate. And the reason is because it's a purely functional implementation. If you think about it for a while, there's actually no way you'd be able to put the head of a list into the tail of one of its sub-elements without a modification. So if we're dealing with an immutable data structure, you actually can't put a cycle in it, which is bad if you need to do that, but it's mostly good. Anyway, other than termination of the types, just writing this doesn't prove much of anything about length here. But you notice when you're using these match expressions, it is a pretty reliable way to code. It forces you to handle all the cases. What if this had several different things it could be, right? And I hadn't matched on all. Actually, it's going to fail out then. It's not going to let me match on just some of the cases. I could do just a wildcard at the end, right? And then it would let me. But other than that, so it's a pretty nice construct to use for that reason. You also see that in Rust and OCaml and things. But this implementation is actually so basic that I contend it serves as kind of a mathematical definition of what a length is. We could just sort of take this as an axiom and let's use it to prove out other implementations. For example, what if we wanted a more efficient implementation? This is doing recursion. So, maybe if it's not optimized properly, then it's going to blow the stack up. We wouldn't want that. Now, let me make a point here. because it's actually not true, given the Dafny implementation currently, that that would be a problem. So I can put tail recursion true, kind of like a compiler hint, and then this would fail if this were not an implementation that could use tail call optimization to get rid of the stack growth and the recursion here. I'm not going to fully explain tail call optimization right now, so you'll have to look that up if you're interested. But in order to be a proper tail call, you have to return the actual result of the recursive call directly. You can't like add one to it. So the compilers had to do some operation in order to make this a proper tail call. In this case, it works, and this annotation proves that. Let's say that that wasn't the case. I'm going to show you how that often would be implemented. There's a technique called an accumulator you can use to kind of transform this into something that would be a proper tail call. That may be what the compiler is doing behind the scenes here. I'm not sure. So let's take this implementation and make another one here. Let's say length with an accumulator, and we'll actually wrap that in our second implementation of length. So let's give it an accumulator, which will also be a natural number, is what we're building up and counting. The way accumulators usually work is you call them with a 0 or an empty value first, and as the recursive calls go along, it calls itself with, increasing values in it, for example, as the result is being aggregated. So it's almost an identical implementation to this, except it's going to call itself, and we'll make it a tail call, and we'll just say, I'm going to send in ACK +1. So now this is a vanilla tail call implementation that we'd be able to move over into any number of languages. If they support tail call optimization, then they will be able to, at compile time, expand this into a loop, and you're not going to have the stack growth inefficiency that you would have in other kinds of recursion. There's also a bug in this implementation as I've naively transformed it. Do you see it? See if you notice it, but the beauty of it is we don't even have to notice it, because we're going to prove that this matches our canonical implementation, and if there are any bugs, that will be exposed. First off, let me just make the wrapper definition so we could see how this would look like if we were delegating to it in a real situation. We wouldn't always want to have to start calling it with 0. So I'm going to make length prime, just another implementation of length. And it will also take a list. It'll have identical signature to the other. And then we'll simply we'll delegate to length ACK for accumulator with 0. All right, cool. This is where we start diving into Dafny's pre and post condition syntax. This is a post condition. Ensures length prime li equals length li. That should always be true. Is that true? No, we cannot prove it. Not really sure if that's because of a bug yet, or because there just aren't properties on length ACK yet to kind of bootstrap this off of. So let's go further down, right, and see what we can do here. Now, what ought this equal? Length ACK of li and any given accumulator, that should equal the canonical definitional length we'll use, the length of that list plus the accumulator we're passed in. Now, it zeroes in on, I cannot prove that in this case, so let's scrutinize this line, and case nil returns 0. So actually, that ignores the accumulator. That was the bug I was mentioning. So if I say in case nil, we return the accumulator, now this is proven, and this is proven. So now the ostensibly more efficient implementation, maybe not in Dafny, but in many languages, this accumulator style would be more efficient here, has been proven equivalent to the easier to understand canonical implementation. Another common thing to do would be to do an imperative implementation instead of a recursive one. And again, in Dafny, we can prove that an imperative implementation matches a functional one. That is made very easy. I did that in the Gilded Rose video, but I'm going to do it a little differently here, because you can define a method, which is like a function, but it can modify things. And then as a post condition to that method, say that the return value needs to match what this other function is. So you're kind of giving an alternate implementation. But that's such a common pattern in Dafny that there's special syntax for it too. So we'll do that this time. We'll say function length. We've got a functional implementation. And then say by method. So this function definition is going to be like the specification, and then the method's going to be the implementation. So how would we implement this in a loop? Pretty easy, right? This is kind of your textbook, initialize I to 0, the beginning of any old school program. Going to make something to navigate the list with. We'll call it pointer, and we'll initialize that to li. Well, pointer is not nil. Then we'll just iterate through this. So we will increment I every time we go through and pointer's not nil. And then we'll reset pointer as well to pointer.tail. We know that pointer has tail because pointer's not nil. So the data type should be satisfied. Afterward, we'll return I. So that looks right, but it's red. So it says could not prove termination. Okay, try supplying a decreases clause. So it was not able to prove to itself, though I believe it is the case that this loop will always terminate. It couldn't prove it by itself. So I'm going to give it a hint about how it should think about why this loop is terminating. So this decreases pointer. Okay, we got our loop termination. What is wrong now? So it couldn't prove post condition about the return value. So there's a bit of a learning curve with knowing what's going wrong in these situations, why it can't establish that these are the same. But given that there's a loop here, it's typically the case that you would need to add an invariant. So we know that some property holds, at the beginning, at each successive iteration, and then finally at the end. We want an invariant. So what should be true? Now, what do we have access to? We have pointer and I. Pointer represents one of the nodes somewhere in the overall linked list. And I represents a count of how far we've gotten into it. So it should be the offset of pointer relative to the head of the list. Now, I think that should mean that the length of pointer plus I is equal to, now don't worry about efficiency as far as are we, iterating in the list. It's not actually done at runtime. So invariant is not a performance concern, except for compile time maybe. So again, length of pointer plus I ought to equal to the length of the overall list. It establishes that invariant, and that gives us what we need to get overall verification here. So this is the implementation that will be used at runtime, and this is the functional definition, and we've shown that they match. So if we look at this, we know what this does without even looking at it. So that was kind of a deep dive into a couple of ways that we can get assurances on various implementations of length. I'm not going to do that many combinations with the rest of these, but let's just go through and implement these other verbs here. So we've got get, and I'm going to use this to get me started here. So we want to get something from li at a particular index. What do we want to return? Not a nat. We want to return a t where it's a list of t. So we'll use generics in the function definition. I'm not returning the right type yet, but that's okay. We'll get there. So case nil. Now this is an interesting notion here. If I'm trying to retrieve any index and I've got nil, even if the index is 0, like I'm already off the edge of the list. I have no element to return. Do I throw an exception? That would be a familiar way of handling this. That would violate the type system here. That's not what we're doing. We say we're going to return a T. We have to terminate. We have to return a T. So there's a couple approaches we could take here, depending on whether we think it is a valid invocation of this method to walk off the edge of the list. If it's not, we could use preconditions to forbid it. If it is a valid way, then we could go from a T to a maybe T. Let's explore that way first. So this would be more in line with what you're used to seeing of like, well, this might succeed or it might throw an exception or turn null or something. It's got a failure mode. We'll do that, and then we'll show you how you could avoid that if you didn't consider that valid. So let's construct a maybe type out of thin air. If you included the standard library of Dafny, there would also be that in there. So maybe T is either none or it is just T, just a T. That's a common way of doing an option type. So that was an easy definition. We go back down here. What does that let us do? We're not going to return T. We're going to return maybe T. If we've got nil passed into us with any natural number, that means we've walked off the edge of this thing. So we're going to return none. We can't get your index. Now, what do we do if it's cons? It's got a head and a tail. Well, again, there's two possibilities. So we got to break it down further. I might be 0. So if we are at a point in the list where we're being asked for index 0, then we can just return the head of the list, right? We're there. I equals 0, then head. Else, now what do? Well, we recurse, right? So get from the tail I minus 1. All right, that's type error. So if I equals 0, return just head, wrap head in a maybe. And again, I might wonder, is this properly tail recursive? So I can put that annotation on, and yeah, again, it verifies, so we know this is a pretty efficient implementation as far as a linear traversal is going to go. But I mentioned, this gives you the possibility that it might return nothing. So let's make that an alternate implementation, and let's make the primary version one that will always ensure that you're getting a legitimate index here. And this time it's going to return a proper T. And I'm not even going to handle that case because we can't get there. Head. Now, as you can see, it doesn't accept that. It doesn't think we've handled enough cases because it's possible to call this with an I that's too high for the length of the list. But we've only done post conditions so far. This is where we can introduce a precondition. It requires that the length of Li be what? Does it need to be greater? Let's imagine the base case to make sure we don't have an off by 1 error in our thinking. If we have a list of one element, its length is 1. Then the most that we can index on it is 0. If we have a list of length 0, we can't even get element 0. So I'm going to say length of Li has to be greater than I. If we require that, now this is proven to terminate. This is proven to handle all cases. So that's cool. That's not a complete correctness proof of this because it, might be giving you the wrong element or whatever. Something we could do is put specific test cases into what's called a ghost method and put an assert on them if we wanted to get specific cases or arbitrary parameterized cases tested here. So that was a lot to absorb for today. I think next time we'll swoop back and cover these last 3 verbs. And we'll show how to specify them with more emphasis on the pre and post conditions features of Dafny, as well as being able to sort of define these in terms of each other and how they ought to behave. We've already seen numerous ways on the code so far where we're able to attain far higher assurance than we're used to having at compile time. So see you soon. Subscribe if you like. And as Lao Tzu said, with patience, the most tangled cord may be undone. Thank you.